Okay, so what I'm going to show you here is how to solve this problem, and then using chi-analysis or chi-square, we're going to be able to accept or reject this hypothesis or this data. So what we're going to first start off with is there's 60 flower plants that are planted in a flower bed. 40 of them are red homozygous dominant, and 20 of them are white flowering plants. So what we'll do is we'll take 20 and we'll divide it over 60, and this is going to give us 0.33, and this would be the q square number. So in order to solve for q, we have to take the square root, and when we do that, we get 0.57. Now from here, what we can do to find p is take q and subtract it, and we will get 0.43. So p is 0.43. Real quick check, 0.57 plus 0.453 will give us 1. So we know that is true. Now what we can do now is solve for p squared plus 2pq plus q squared. Now for the sake of time, I'm going to go ahead and give you these numbers. This would be 0.33, that was our initial number. But if you are still not understanding this, you should probably resolve it on your own. Q squared would be this squared, so we actually get 0.18, and 2pq, so 2 times this will give you 0.49. So what you'll do now is you are going to read the next set of data and see what we have here. So in a subsequent year, after the flowers have gone through and repollinated themselves, you have 178 red flowered, 190 pink, and 52 white. So what you'll do is you actually will add all that up. So 178 plus 190 plus 52, that's going to give you 420 total flowers. And that will be used in a minute. So what we have to do now is we have to use the data that we pulled from the initial, because that's giving us our frequencies that we're going to use. So what we want to know is how many are red, how many are pink, and how many are white. So what we do is we take these frequencies right here, so 0.18, 0.49, 0.33, and we multiply them by the total that we now have, which is 420. So we take 420 and multiply it by each frequency. So what you should get is 75, 206, and 139. So what this is going to tell you is this is your new numbers, or your expected number that you should see based off of those frequencies. So what we actually have to do is we are going to use those numbers and continue on solving for the chi-square. So what we're going to do is you're going to make just a small little table. So this is observed, all right, this is expected, and then this will be your observed minus expected squared over your expected. So initially what we had observed was 178 red, 190 pink, and 52 white. So what we'll do here is we'll actually take our expected number that we got, so 75, 206, and 139, and what we're going to do is use that in the last part. So what you'll work out is 178 minus 75, square that, divided by your expected, which would be 75. The next one would be 190 minus 206 squared over 206, and the last one would be 52 minus 139 squared over 139. So what you'll actually get when you work this out for this column should be 141, 1, and 54. So our chi-square analysis is a number of 196. So if we actually go back to thinking about degrees of freedom, we have 3 sets of data. So 3 sets of data, and we subtract that by 1, we actually have 2 degrees of freedom. So going back to a chart, I was supposed to print this out for you, but if you want to just look up one, we're going to do a 0.05 analysis or difference. And if we look at degrees of freedom, I'm just going to draw like a quick sketch of this. We should have these values, and this is consistent with any chart that you look at. I just didn't print one out for us. So what you'll do is you'll look at this chart. So if we have 2 degrees of freedom, we should expect to see a number lower than this. But what we do see is that our number is 196. So we obviously know that is way above 5.99. So based upon that, we're going to reject that this population is in Hardy-Weinberg equilibrium. If it were, and we worked all this out, we would expect to see a number lower than 5.99, and then we can go ahead and say that that population is in Hardy-Weinberg equilibrium. However, what this does show is that there is evolution. And how you can tell realistically is if you look back at the problem, you only had red and white, and now you have pink. So you know that is a new allele within that specific population.